Okay, it should be working now. Is it visible now?
Yes, sir.
Okay. Okay, I'll just start over. So, hi everyone, to all of you who joined later. I'm Sagnik. I'm a PhD student in IIC Bangalore, and I'm helping out as a TA in the machine learning course. So, this is the third session which I'm taking. I'll discuss week 4 content this time. So we'll go over weak theories, generalizations, decision trees, and cluster analysis. And then, if you guys have any doubts, we'll try to clear those. Right. So I'll start off with weak theories. So a weak theory is what we usually encounter in machine learning, which is focused on creating theories or abstractions uh, from from a large set of instances. So we have a large data set, but we have a very weak or almost no background information or prior model which we can work on, right? So the thing with weak theories, they require a lot of training instances to create a satisfactory model, and if you don't provide the sufficient data, then it is not going to work out, right? And in contrast, a strong theory is usually used to create or modify an existing model, right? So we have, by existing model, I mean we have a prior knowledge of this model, and we want to improve our understanding of this model. So that is a strong theory comes in, and for this a smaller set of training instances is sufficient, right? So that was all. Now moving on to generalization. So the main objective of generalization is to formulate a hypothesis. So you want to create a hypothesis which is consistent with our provided data. So we start off with a data set which has a set of positive and negative examples or instances, and our objective is to generate a hypothesis which is consistent with this data set. So all the positive examples in the data set are classified as positive by this hypothesis, and all the negative instances are classified as negative by this hypothesis, right? So what do we need actually to like to make this generalization work? First of all, we need a language to describe the instances. So the instance language and the hypothesis language, right? So by language, I mean you need to have some sort of representation of the instances and how you want to represent the hypothesis. And the second thing we need is a matching criterion, right? So how do we tell, like uh, so as humans, as we solve the examples, you'll see that we can just tell that okay, like these two things are similar, but a computer must have some sort of metric by which it can some sort of metric or criterion by which it can test whether the uh, so what the hypothesis classified and what the original classification is, so the two must match, right? So it the computer needs to have some sort of criterion through which it can match, it can correctly match an instance, right? The hypothesis space actually, so it is formed of concepts or these small uh, like generalizations which are ordered from more general to more specific, right? So here in this example the arrows are in the opposite direction as we are building up this generalization. So in order to build up this sort of generalization, we so we have to start from nothing and then we go up to this massive generalization, right? And so this hypothesis space actually is found of concepts which are ordered from more general to more specific. Usually, that the kind of tree, if you call it, is written like the most general thing is written at the top, and then this is more specific and more specific like that, right? So so this sort of ordering is called it's a partially ordered set. This sort of ordering is not called partially ordered. By partially ordered I mean that, so see here, we start with nothing. We have these three new concepts x, y, z, and we form three additional concepts as combinations of these. So x, y, x, z, and y, z, right? So you see that this X is connected just to this and this. Okay, so it is not connected to YZ. So it is not so this connection does not exist, right? Similarly for Y, this connection does not exist. For Z, the XY connection does not exist. So like since since one member here is not connected to all three members in the previous layer or in the next layer, however you may call it. So that's why it's called partially ordered. If it was connected to everything, then it would be a fully a proper ordered set, right? So again, so this connection is like you can call it an ordered set connection. So all three are connected to XYZ, but in the middle, so this is what makes this entire set a partially ordered set, right? So there are three data-driven strategies to find the generalizations, which was discussed in the lectures. One is depth first, then breadth first, and the version space approach, right? So, a moment. Okay. So what we'll do is we'll take this example. We have four instances. Two are positive and two are negative, right? Okay. Two are positive, two are negative, and we'll try to build a generalization using the three approaches. So depth first. So first we'll use depth first, right? So I'll write them down. First we'll use depth, then use breadth, and finally we use version space. Right. So in depth, you start off with the current best hypothesis. I'll not solve it initially myself. I want you guys to work on it. So in depth, you start off with the current best hypothesis, and you work towards getting all these classifications right. So can someone tell me the answer basically? So what is the so what would be the current best hypothesis at the end? So what would be the best hypothesis that we get basically? It should not be very difficult. Like I'll give you guys 3 4 minutes to solve it, and then I'll.
The current best hypothesis actually has negate the, I mean, give a general thing for negative things, no? We should be moving more towards a positive.
So yeah, it has to like so if it
So the,
encounters.
a wild card and then the brown horse, and a wild card and a brown horse could be one current best hypothesis, because
So you're saying so I have
angry and happy
some
both is
wild
not
card.
possible, no?
So
So
wild
wild
card.
card, brown horse
So brown
or
horse.
brown cow, yeah.
And along with that, you want.
Wild card, brown horse.
So this was horse. I'm not writing
Uh,
horse. So wildcard brown horse and wildcard brown cow. You're saying.
Brown cow, yeah.
Okay, so this is not in line with our first positive instance. So this will like our first positive instance is not part of this generalization, right? So we have a black horse and a brown cow. Right, so brown cow fits, black horse does not fit. So angry and happy is so that can be anything.
No, how it can be angry brown horse and a happy brown horse? Angry brown horse and it can be a happy brown horse.
Yeah, but
It can't be both, no?
it can be angry brown horse and happy brown cow or whatever. But but that is my first positive example, which is a angry black horse and a happy brown cow. So this positive example is not covered by this generalization, right? So this generalization will incorrectly classify this as negative. So this first
So
example is
can
negative.
it be wild card and a black horse, a wild card and a brown cow,
Wild card, black horse, and wild card,
wild card, brown cow?
brown cow. Right. Yeah, so this is actually the correct answer, but I want you to tell me how you reach this conclusion.
Yeah, because this more specific to general. So this
Hmm.
depth first, unlike the breast first, goes in the opposite direction of
Yeah,
more specific to general.
yeah, that's right. So, how did you start off with? So, how do you start and how do you end? How do
We
you?
yeah we start with yeah, I'll just tell you. You start with a negative instance, and then
So, okay.
it is the negative instance and the current best hypothesis instance matches.
Yeah. So,
Then considering the ways of making current best hypothesis more specific,
yeah. So, in this
right?
case,
Instance
so
no longer matches.
what is my first step in this case? So I have just in my so my problem is I have just these four instances and I want to create a generalization. So how do I start?
You identify the negative instance first,
Yeah.
and
So
then
I already
we
have
try to
those.
yeah.
Already
So we
have
match
those.
that
We match that too. I'm sorry.
current best hypothesis.
So what is my current best hypothesis?
This wild card and
So
black
how did
horse.
I get this?
That's a more general version of the
So do you
specific
just guess
situation.
this in
Uh,
the? I mean, this is the final thing which we will eventually come to. But my goal is to get this. You can't guess this. So you can't keep guessing like different things and then try to match it because that is a very time consuming process and like computationally expensive process obviously and you will like it might be that you get a generalization which works in your first try but in this case okay I have only like three features like this mood color and animal, right? So if I have more features and more number of animals even, so this would be kind of an impossible task to accomplish to try to even guess this. Like how do I start? So what is the current best hypothesis in my first attempt?
The current best hypothesis should match that instance one, no? More or less one or two.
It should like it should match both 1 and 2, right? Because both of them are positive and it should not be matching 3 and 4 because both of them are negative. So now that I've been given these four instances, so you're saying we choose a negative instance and we compare it to the current best hypothesis. But I have not given a current best hypothesis in this problem. So how do I even come up with a with so what is the first step? I have to assume a current best hypothesis, right? And then I can like compare it with negative or positive examples. So I'll tell you the easy way to do it. The easy by easy I mean the most foolproof way to do it, which is in the so you see instance one, so immediately you assume it to be the current best hypothesis, right? So my current best hypothesis right now is angry black horse. So in the first iteration you can call it uh, whatever, angry black horse and a happy brown cow, right? So I start off with this. This matches my first positive instance. So this is good. In instance two is also positive, but currently my CBH is not matching instance two. So I have to make my current best hypothesis more general now. Okay. So how I can do it is
One more wild card.
yeah,
Then the
so
case
I will
of
start making this more general, which is we'll start adding wildcards here. So what I'll do is, so from here there are like there's one possibility, which is I can go for, so in my second thing I can go for, so say I go for angry and two wild cards, right? Because I see angry is matching in the first card, and I go for happy and two wild cards, right? So this covers my first and second instance pretty well, right? So this is a generalization which works for both my positive instances, right? So works for both positive, right? So this works. But now in my third case, I now encounter a negative example. So in the negative example also, you see there is angry and any two wild cards, happy and any two wild cards. So this generalization is also will also be classifying this third example as positive, so which is incorrect. So I need to go back, right? So from here I need to go back to this, and I have to find out if there is any other generalization which is possible, right? So another generalization which both of the positive instances have is, so I go back and in my second case I change it to, so say wild card and uh, brown cow and a wild card and black horse, right? So now when I go to my third case, then this does not match anymore. So wild card and brown cow does not match. Wild card and black horse also does not match. So this is classified as negative. So this is also done. And the fourth case, angry brown cow does match this one, but here we have happy brown cow, so that does not match. So the fourth case is also, so the third case is doing good with this, and the fourth case is also looking good with this, right? So now that I have covered my four instances with a theory, with a generalization which can, account for all the positive and negative examples, so I'll call this my final CBH basically. So my final CBH will be, yeah, which you correctly said was wildcard black horse and wildcard brown cow. I mean, the order of these two, I mean, matlab sets does not matter. It can be whatever order you want. So this is the current best hypothesis. Does anyone have any doubts? I'm sure there's some doubts in this approach.
So it is like we are always backtracking to the earlier version of
Yes, we have.
CBH.
If the negative example does not match, is if the negative example is matching any generalization, we have to go back and, uh, you know, so we have to go back and make uh, our so this the reason why the third instance matched with this CBH is because this is too general, right?
Hmm.
So we have to make, so we go back to our more specific case, and we try to think of some ways in which you can make it more specific. You don't have to go back here, like it's not really going back. You can consider making your CBH more specific, so that your previous positive instances should be matching it, and your current negative example should not be matching it, and your previous negative examples also should not be matching it, right? So in this case I have it ordered like positive positive negative negative. So if it was like positive negative positive negative, then I would take one instance at a time and try to see if my generalization is working. So for positive CBH, my generalization should work, and any previous negative example or should not be included. Any previous positive example should be included, right? So in the second case also, I have it positive. So once I have modified my CBH to match this, I should check whether if it is also matching my previous positive instances, and also matching and also not matching with any previous negative examples. Right. So you may be modifying your CBH in every step, but you have to keep checking the previous instances, that whether my CBH is is going to incorrectly classify anything or not, right? So that step has to be there. That is why we went. So in the third case, we saw that this negative example was being classified correctly. So we went back and tried to in so not for this, for this CBH, for this CBH. So when we use this CBH, this is the one I'm boxing off right now. So when we use this CBH for our third example, we saw that it was too general. It was classifying it as negative. So we have to make it more positive, right? And the best way to do it is just go back to your more specific case and try to make that not as general as this, a little bit more general. So more specific than this, right? So that is how you kind of think of it. So I mean, this is how you so this how we think about it is like this. So mostly if you have it in an exam, you will have a smaller data set, but in a computer you will follow a proper so I think yeah, the professor had presented a pseudocode for every search strategy. So we'll actually turn that into code, and we'll use that code to do all of these computations, making more general and more specific like this. Okay, so that is how you do it in depth first. So are there any more doubts in this?
Why in the second case it should be more generalized in the sense like why did we come at that? It would have been
Okay, so in the
like
first
angry. Yeah.
case, yeah, in the first
First.
case, we start off with our first instance as our current best hypothesis. Okay, so we always do that. This is part of the algorithm, right? So
Yeah, that is fine.
yeah, so when we reach the second case, so now I have to. So angry, my CBH was angry black horse and happy brown cow. So, and my second case is angry brown cow and happy black horse. So this does not match my CBH, right? So I have to make my
Mhm.
CBH more general to account for this positive example. So how can I do that? So the first suggestion is to make it angry and two wildcards, happy and two wildcards. This matches, but this new CBH now, this will also work for the third case, right? So my third instance also gets correctly classified, angry wildcards and happy and two wildcards. So we see that this negative example is being accounted for. So I have to make my CBH more specific. So this CBH has to be made more specific, right? So how can I do that? I can just go for like wildcard and brown cow, wildcard and black horse like that. Okay, so this if you see, like, this generalization is more specific than this one,
Yes.
right? So this CBH is more specific than this, but it is more general than the first one, right? So
Yes.
we have reached kind of a middle ground between 1 and 2. In this case, both the positive instances are being correctly classified, and the third negative example is also being correctly classified. Okay, so now we move to the fourth example. So fourth example, thankfully automatically it will also be classified as wrong. So angry brown cow, so angry brown cow matches, happy brown cow does not match. So there is a white card and black horse here. So the fourth example is also correctly classified automatically. So we don't need to change our CBH anymore. And yeah, so finally we have our best hypothesis for these four examples, right? So this was depth first. Asha, do you guys have any more questions?
The order is immaterial, right? Whether you take
Yeah,
the.
yeah, yeah. I mean, black horse. I mean, if it was wild card brown cow, wild card black horse, these two can be swapped. Like, this does not matter.
Yeah.
Okay, so we'll move to bed first. Then I'll do it in the next page. There's no space here. Uh, okay, yeah, I'll do it in the next page only. So I have to keep coming back to this page. Anyway, so the just wipe some of the things from here. Okay. So okay. Now we come to bread first, right? So in bread first, what we want to do is,
Specific to general.
yeah, it's specific to general. So the yeah, I mean, I want you guys to do it first rather than me doing it.
Yeah, wild
Yeah,
card,
do the different
black
color.
horse, and a wild card, a brown card.
I mean, the answer will be same, but how do you get to
Answer
it?
is the same.
Answer is the
Yeah.
same. Okay. So this will always be the answer. Now that we have done it through depth first, so this is the answer in every case. But how do you get to this answer? Like, what
Yeah.
is the
So
process?
it is that if it is a negative instance, then retain in the subset those generalizations which do not match I.
Yeah,
So the
that is it.
those generalizations which do not match the instance are that only, which are the
So
negative instance.
yeah, but like, how would I start? Like, how would I start here? Like for depth first, we started we said that
You
we'll call
start with
instance
the
one
most specific
with
generalization.
yeah. So in this case also, like, since you have instance one positive, so we'll start with this as our more specific generalization, right? So we'll start with this as what we call S1 basically. So whatever I'm writing in blue is for breadth strategy. Okay. So this I'll start with S1. I'll call it. Okay. So this is angry black horse and happy brown cow. Now the next step is to create like so my next example is also positive first of all. So first I check for whether it is positive or negative. So I have my positive instance. So I'll generalize S1 so that this positive instance is also accounted for, and I have to create as many generalizations as possible, right? So for this case, if you see, so what can I go for? So I can
Same
go
question mark, black horse, question mark, brown cow.
yeah, this is one.
Wild card,
Yeah, question mark, what is
brown
it,
cow.
brown cow? Yeah, this is
Or
one.
you can swap it, that question mark, brown cow, and that wild card.
Sorry.
You can write first the brown cow and then the black horse.
No, that is the same thing.
Yeah, that's the same thing.
Yeah,
So you can have uh,
I need to have two different. I
yeah,
I can have two different generalizations, right?
yeah,
Two or
you can
three,
have
whatever.
angry question mark,
Yeah,
and then the happy question mark.
yeah, that's right. So from after my S1, so I will make these two from S1, right?
Yeah,
So I'll call
that is
this set
S2.
as S2, right? So both of these together are called S2. Now my third example is negative again. So yeah. By the way, S2 will work for both positive instances. So I have this covered now. That I am sure that uh, so whatever like all my previous positive examples have been covered, and none of my previous negative examples are being covered with S2. So I'll go for instance 3 now, so which is negative. So now I what I have to do is if this negative instance is matching any of these two this thing the generalizations, then I should remove it from my S2, right? So if you see here, this and two wildcards, happy and two wildcards will match this negative example. So what I'll do
So
is
that's why
I need to
you
remove
try to remove
this.
it.
Yeah, I need to remove this. And from so S3 basically, S3 will be just this wildcard black horse and wildcard brown
Wild card,
cow.
brown cow.
Yeah, and finally I'll go to S4 4, I mean my fourth example, and this is also, thankfully, it is automatically being negated by this S3. So S4 is also the same as S3, right? S4 is this, my final my final set of, so final set for breadth first. So breadth first search is this S4, right? And what this breadth first strategy does is, at the end, it will give you all possible generalizations which work for this particular data set, right? So in this case it was only one, but so you see, from S1 to S2 we went to two generalizations. We might have had like 4 or 5 generalizations here, and then when you encounter one negative example, maybe one of them goes away, and then maybe another one goes away. So we're still left with three like generalizations which may work for this entire data set, right? So this the answer to a breadth first search is always a set of generalizations which work. Okay, it will not give you only one answer like depth first. It will always give you a set of all possible generalizations, right? And yeah, and in this case also, if you see this S4, like this set is the same as the previous one, right? So our answer is the same. Does anyone have any doubts? Yes. Sorry. Mm, this include, slightly no. Depth was in red, breadth I'm writing in blue, and yeah, for version space I think we need to. Um, so what I'll do is I'll quickly just copy paste this. I'll quickly copy paste this to the next slide so we can work on version space. Okay. Okay. So yeah, so we want to work on version space now. Yeah, so what would you get in version space? So remember, in version space, I will always get two sets, basically two sets of generalizations. So one is the specific, so S set and the G set, right?
Yeah, the S set will be the same as this,
Yeah, S will
and
be
then
same.
it is similar to breadth first strategy where you're going from specific to general,
Yeah,
and the generalized thing can have uh, wild cards, more generalized
yeah, it will be more
because
generalized, right?
so what's there is a black and the cat, something. These things are actually sorry, angry and not angry, brown and horse, something. Those things are specifically can be defined, or the other things can be generalized.
Yeah, so
There can
what
be
we'll do is,
more wild cards playing actually.
so the G set will always have more wildcards because it is the set of generalizations. Right. So, so with I'll tell you right from the get-go that with only these four instances, we won't complete this version space approach. So the ideal version space completion a criterion is SNG should become the same, right? So we make our generalizations more and more specific so that it approaches a limit, and our specific set we make it more and more general in every after every instance so that we reach the same limit. So at the end, these two become the same, but with only these four examples we won't get there. So we'll get to a particular level. Let's see. So anyway, so in every case, so instance 1 will be my S1, right? So S1 is what is it, angry black horse and happy brown cow, right? So this is S1, and what will be G1 then? So G1 is the, so we'll always start off with the most general case, which is all of them are wildcards, right? So this is what we start off with. Now, so for so the next example which I encounter is a positive example. So sorry. In that case, what I'll do is for S, what I have to do is I have to make some more generalizations so that it matches, right? And I can again like create these two generalizations, right? So one is wildcard black horse and wildcard brown cow, and the other is angry and two wildcards and happy and two wildcards. Okay, and so what I need to do to G1 is so we started off with the most general case anyway. So G1 will just go to G2, right? So G2 is the same thing, right? So after my second example, also this remains the same because it matches my positive instance anyway, right? So these are two. So this is S2 now. So both of these form S2, right? So both of these form S2, and this one thing is G2. Okay. Now I'll move to the next example, which is a negative example. So if I encounter a negative example first, so from my S set, I have to remove the generalizations which match this. So I will remove this, right?
Yes.
So from here S3,
And
S3.
also S4. Both are valid.
S4 also this will be the same thing, but okay, let's just see one example at a time. So this will be, and this will be brown cow, right? So S3 becomes this, and for the generalization I have to make more specific, right? So for G3 what I need to do is so what do I have here? So this brown horse, and brown horse is creating so problems, I think. So anyway, like all of these are creating problems, so I need to get some generalization which works for the previous cases, so which works for the previous positive examples, and it should also be more general than this, by the way. So it should be more general than S3, right? So it's a difficult choice here. Let me see. So
So
what can I
wild card,
choose?
wild card, black, wild card,
Wildcard, black wildcard, yes, that's right.
and
And
generalized.
the next one you're
Three wild cards.
saying is all same.
Three wild
Three
cards,
wildcards, right?
and then
Uh,
wild card.
okay, so this will probably be a different set now. So you only have two in this case. So you want to make a different like set. You can make it once again. Yeah. Sorry. You were saying
Wild card, cow, three wild cards.
three wildcards. Right. So okay. So this works. If you had gone for wildcard horse, no, that would not have worked. Okay. Okay. This works for this case. Fine. Okay. Then for the fourth instance, if you see S3 works for S4 as well. So this is equal to S4, right? So this same thing works. And but in G3 I have to so basically generalize make it more specific, right? So I think this one will not work. right? So this will get deleted because we have like something something cow, right, and something something something. So three wildcards. So this generalization is working for this instance 4. We don't want it to work, so we'll just remove it. But yeah, this one works. So we'll keep this. So black question mark and three wildcards, right? So this is our G4 basically. Okay, so this is our S4, this is our G4, and we have covered all our examples. Everything is correctly classified, so we are done with this algorithm. Right. So does anyone have any doubts?
So if it stops at G3, then the earlier thing would work, no?
Yeah, I mean if it
That means if
stops,
there was no instance 4.
then this would have worked.
Yes,
Yeah,
yes.
then we could have had both of these in our G3. Right. So yeah, so you see, like as you keep adding more examples, right? So as you keep adding more positive examples, more negative examples, this G4 will become more specific. S4, like G4 will move on to G5 and G6, and they will become more and more specific. And S4, S5 they'll also become more and more general, and until you basically can until both of them become the same. So that's when you can terminate your algorithm. So that is the best like generalization which you can find, right? So okay, does anyone have any more doubts? Yes. In general also, so from this topic, in any portion, if you have any doubt, then you can ask me, not just this example. Okay. So I think there are a lot of doubts. So we'll move on to decision trees. So I will discuss a little bit, then we'll do a problem. So decision trees will focus on a particular set of learning algorithms. It's called top-down induction of decision trees. So TDITT algorithms. And usually the way we build decision trees, we'll keep the root at the top, and the focus is to select. So the problem with decision trees is, so there are a lot of features, right, and you don't know which feature you should use to make your classifications, to make your branches, right? So what should be your first feature through which you make two or three branches or whatever. So you don't know that. So that is why we have some metrics based on which we can select we can order these features, so that so we have an easier time creating the branches, right? So the goal of a decision of the final goal of a decision tree is to have the final nodes, which are called leaf nodes. So the final node should have maximum purity in each case. So if they are all from the same class, then that is the best situation. And if they are not, the most of them should be from the same class, and there can be a few parts which are not from the same class, a few instances. So how we measure? So the way we measure uh, like these order of features. So the way we measure the features so that we can order them, the way we measure purity. So they are known as the information gain basically, and they are based on either entropy or the Gini measure, right? So entropy for a particular case, so and entropy for a particular uh, case is calculated by it's a negative of, so C is the like basically the value, right? So just 1 second. So yeah, this is the measure of entropy. So H is called the entropy, and It is measured like this: probability of C into log base 2 of the probability, right? And the gain of S for a feature F. So S is our set basically. So the gain of S for a feature F. So we take the entropy H of S for the whole set, and minus. So the value. So V are the values of the features, right? So for all the values, we'll find the so this is like cardinality. Like this is the number of instances in S which have the value V for feature F, right? Right. So I have a feature F, so it has some particular values. So V1, V2, V3, and SV is the. So if I take V1, so how many? So this will be SV1, right? So how many instances have in S have value V1, right? And how many instances have value V2, right? So this is SV. We divide it by the number of elements in S, and we multiply it by the entropy of SV, right? So entropy of SV is again calculated by the same thing. So C are all the instances, uh, and we find the probability of CV, you can call it there, right? So and similarly, so this is the gain is always calculated like this, and the Gini measure, it is similar to entropy. So these two are related, like they are similar, you can call it. So it is measured as 1 minus the sum of PC square, right? And if you want to find the Gini gain, basically the Gini gain, then you replace this H of S with Gini of S, right? Everywhere. So here also, right? That is the only difference. And okay, so so for creating, so now okay, now that we have our gain, so we'll find the gain for each of these features, right? So and the feature with the maximum gain will be chosen first for the first branch, right? And then we'll move on to the next feature like this. So this kind of algorithm, it's called the ID3 algorithm. Right. So I'll just quickly go through the code. So this is taken from the lecture only. So this so first we'll create a node for the tree, and we'll see that. Okay. So yeah. So if all the instances for this node belong to the same class, then we'll return a single leaf node, right? So we will return a single node uh, at the end of the leaf node with the class label, right? So usually, like for binary classification, it should be like 1 and 0, yes and no, like that. Okay. And when I start my ID3 algorithm again, so if my features are empty, so if I have used all my features, then I'll return a single node with the most common label in instances, right? So otherwise, so this is actually where the algorithm begins. So from here, so first I'll find F. So this is the feature in my list with the maximum information gain, right? So this is where I start, and now so I have my decision features also. So like F will have its own values, right? So for each possible value V, what I'll do is we'll add a new branch with this feature equal to V. So then we'll count the number of instances. There's an underscore here. Okay. So then we'll count the number of instances with which has the value V, and in that subset. So if that subset is empty, then we add a leaf node with the most common class, or otherwise we'll create a new branch, right? And we'll create a new branch. So now in creating a new branch, you call id3 recursively again, right? So you'll call id3, but this time with this smaller subset, and with your current feature removed. Okay. So okay, so let's do an example, then it will be clearer, I think. Okay, so yeah, even this example was taken from the lecture. I could not find a better example online. So we'll just work on this. The decision tree which was created in the lecture was slightly smaller. So like we'll try to create a better decision tree by following this ID3 algorithm completely. Okay. Okay, so first of all, we have to calculate the so this is my target. So this is what so these are my targets. I don't have to calculate gain for this. Okay. So you have to calculate the so we'll use gain based on entropy. So you have to calculate the gain for outlook, temperature, humidity, and wind. Okay, and how you calculate it is obviously I have h of s, which is minus log base 2 p of c, and then my gain will be h of s minus for v f. We'll have some set, and then we'll have my total set times h of sv, right? Yeah. So this is how we do it. We'll go for outlook first. Outlook actually has how many does it have? So it has this like this p of c basically. So that so how we calculate that is like we have here like five. Well, if you count it, so one, two, three, four, five. Yeah, five negative examples, nine positive examples, right? So we'll calculate the gain. First, we'll calculate the entropy, right? So I have nine positive and five negative, right? So my h of my entire set is basically how much is it? So minus of so 9 plus is 14 basically. So 9 by 14 into log this 2 of 9 by 14 plus so I have 5 negative, right? So 5 by 14 to log base 2 of 5 by 14, right? So if you calculate this, I don't know how much it will come. So it is about minus point, let's call it 0.94. Okay. So minus 0.94, and now I have to calculate the gain also. So uh, gain okay, so gain has to be calculated for each of the features, right? So for so if you calculate it for outlook basically, right? No, just yeah, right. So if you calculate it for outlook, right? Uh, um, how it will work is so I have my h of s. I don't have h of s v. So I have three values here: sunny, overcast, and rain. Right. So for what you do to calculate SV is basically like uh, so if my value is sunny, right? So how many do I have? One, two, 3, 4, 5, right? Five examples of sunny, and all of them I think have no, yes. Oh no, yeah, anyway. So 1, 2, 3, 4, and 5. So for SV, right? So for S sun, I have how many? Two positive and three negative, right? So I have total five, and so h of SV will be like minus 2 by 5 log of 2 by 5 plus 3 by 5 log of log base 2 3 by 5, like that. Okay, and h of s is already there. Number of examples in SV is 5. So this is 5, this is 14. So yeah, you get the idea. So like this, so we also have S overcast and S rain, right? So we'll calculate these two values. We'll put them in this summation. We'll do this summation, and finally the gain which we have is I have is calculated. One second. So the gain for outlook will be 0.25 around. So gain of S for wind is, for wind it will be this point so okay, for gain temperature is around 0.03, and gain for humid is point 15, right? Okay, so from these four values you see that the gain for outlook is highest. Okay, so we'll choose outlook as our first branch, right? So the first feature along which we are branching, right? So I'll move to the next page. So I am starting off with something. So I have outlook. I'll start off with outlook, right? So this will have three branches. So one is sunny, one is overcast, one is rainy. So okay, so for every branch we'll look at what the other features are. So first let's look at overcast, because that will be the easiest. So in overcast I will erase all these marks which I made. Okay. Okay. That's not getting just. So yeah. So for overcast, if you see, we have one, two, three, four cases. But if you see the outputs are always yes, right? For this case, okay. So in this case, since all of them have the same um, like output, so what we'll do is we'll just create one leaf node, which is basically yes. So if the outlook is overcast, then you are always going out to play tennis. So like that is the answer basically finally. So, so should you go out and play tennis? If it is overcast, then the answer is directly yes, because all of them have this yes option. So there is no point in checking anything else, right? Now if we go to sunny, right? So sunny has how many? One, two, three, four. I'll move to a different color actually. Here. So sunny, right? One, two, three, four. Yeah, five. So I have five sunny. In this case, no, no. No, yes, and yes. Right, so I have five yes in this case. No, so, sorry, I don't have five yes in this case. So then I need to check the next thing, right? So for Sunny, I will have like so for Sunny, then I
Sunny,
will
you
create
may have to check for
another.
windy also.
Yeah, so the next thing which I'll check is based on these gains. So the next thing which I'll check is humidity, right? Because after 0.25, the next biggest value is 0.15 over here. Okay, so I'll check for humidity first before wind because it has a higher gain. Okay, I will always choose the next feature which has the highest gain. Okay, so for Sunny, I will now check humidity, right? So humid also has like two branches. So it will be, I think it has, okay, it is high and normal. So high, I will underline this. So the ones which are underlined are the features basically. High and normal. Okay. So let's check for high. So Sunny. So the thing is now we have to check only for the blue underlined things, right? So Sunny and high. Uh, Play tennis is no. Okay. So Sunny high. Play tennis is no again. Here also Sunny and high. And play tennis is no. So for the second layer, so like when I check humidity, if I have high humidity, then the answer is always no, right? I have three cases with high humidity, all of them have answered no. So then this now becomes a leaf node, right? With no. Okay, and again, so for normal, if you see, where is normal? So you have to see sunny and normal, right? Sunny and normal, this is yes, sunny and normal, this is also yes. So both of them have the answer as yes. So sorry, this will again become a leaf node with yes, right? So this classification is done on the sunny side. Let's move to the rainy side, right? So rainy side again, we'll check humidity, right? Because that has the next highest entropy after outlook. Okay, so humidity. So again, it has two options. So sorry, just ignore that. So I'm writing it here: high and normal, right? So for I will again erase all of these marks. Okay. Okay. So yeah. So now I have rain, right? So I'll underline the rain ones. There are five here. Then we'll see with high humidity, right? So rain and high humidity. So this answer is yes here. Rain and high humidity is normal, normal. This is also normal. Rain and high humidity. The answer is no. So basically, I have to look for this is inconclusive, right? So I have to look for another feature. So next feature which I will look at is from my this thing from my gain. I can tell the next feature I should look at is wind. Okay, it has 0.48 of 0.048 over 0.03 of temperature. So next thing I look at is wind, right? So rainy, high humidity, weak wind. Answer is yes. So wind also has two parameters here, so weak and strong. So the if the wind is weak, then the answer is yes. If the wind is strong, then the answer is no. So I can create another like thing over here, which is wind, right? So this will also get created here probably. Let's see. So it is, what are the two things? Weak and strong, right? So weak and strong, and these only have one answer, so this one is yes, and this one's answer is no, right? So this side is done. For normal humidity, rainy and normal humidity, let's see. So rainy and normal humidity, this is yes, rainy and normal humidity, this is no. Any more? Yeah, rainy and normal humidity, this is yes. So I go for the next feature again, which is wind. Okay, so wind. So if the wind is weak, answer is yes. Wind is strong, answer is no. And here also wind is weak, so the answer is yes. So if the wind is weak, then our answer is yes. Wind is strong, answer is no. So even in this case, we'll have wind and two options. So I should have written down the number of items in each case. Okay, yeah. We'll do that. So this is yes, and this is no, right? So we'll just quickly go back and count how many yes and no we found. Finally. Okay, so for overcast it was, how many was there? One, two, three, four, four. So four items are here, right? Four of my data items are here, right? They're classified as yes, means like four of my data items are currently in this bucket of yes. Okay, so in this bucket, how many do I have? Sunny and high, right? So sunny, high. Okay, there are three here. Uh, Two more are sunny and normal, which is in yes. Okay, okay. So this has three of my items. This has two items, right? This one, so rainy, high humidity, and weak wind, right? So rainy, high humidity, weak wind, rainy, high humidity. Okay, so rainy, high humidity, and weak wind only has one item, right? So this is one item. Rainy, high humidity, and strong winds. So rainy, high humidity, strong wind also is only one. So this also has one item. Then rain normal and weak. So this, how many does it have? Rain normal and weak has rain normal and weak has two, right? So these two items. Rain and strong. Rain. Sorry, what? Rain normal and strong. Sorry, rain normal and strong. So this rain normal. Yeah. So this has only one item.
So matching a total of 14.
Yeah. So if you add them up, add all the leaf nodes up, all the squared ones. So they'll add up to 14, right? So 3 plus 2, 5 plus 4, 9, 10, 11, 12, 13, 14. Right? So they'll always add up to. So this is a check if you are creating a decision tree. So this is a check you can implement, right? That in the end, whatever yes, no, true, false, 1, 0 classification you make, you count them, how many are in each bucket, you add them all, they should add up to the total number of item like instances in your data set. Okay, so does anyone have any doubts about creating this decision tree? Yes, that small thing. Okay, I don't think there are any doubts right now. So yeah, I'll just quickly summarize. We started off with the maximum gain feature, right? We moved on to the next feature which had so if this feature has a particular value for which all items have the same, like all of these all the instances with this value have the same outcome, then we just directly classify it, right? There's no point going for further classification. Otherwise
We
we'll
don't
move.
need to calculate also, right? Because it is directly showing that outcast means it is you can go and play. Do we need to calculate information gain because it is showing it
No, no,
outcast
no.
is
So so the gain you need, so the gain is calculated only for the features, right? So here I have how many features? One, two, three, four features, right? Four features. So for every feature, I will have a particular amount of gain, right? Not for each feature value. So here you see the gain are only for these four main features, right? In the set.
my point is that
Ha,
when there is outlook has got the four outcomes. I mean there
ha.
is a four target and is yes. So we can directly go creating a decision tree with the outlook, right? Na? Start with outlook.
Yeah, but
Overcast,
okay, like
overcast feature.
I don't get it. Overcast is a value of a feature. These are the features.
Yeah, overcast has got
Huh.
the maximum possibilities. Na? Four are there, no? So we can directly go instead of calculating and checking which one to start with. Information gain is 0.25 here, but
Yeah.
directly you are seeing that there are four the four outcomes which are
So
yes.
yeah, here you can see it. But what happens when you have a data set with 50,000 entries maybe, and you need to
Yeah.
create a decision tree out of that. So this is for like this if you do this, you can scale up very easily. Like it does not matter what the size of your data set is anymore, right? Like you can have 14 entries, you can have 14,000 entries, and it would not matter because you are always following a like following the mathematics. So you calculate the gains for every feature. So maybe you have 10 features or so, you will have 10 gains to look at. Okay, so the calculation of this gain is like very cumbersome by hand, but for a computer this is like this is very trivial for a computer, right? Just this maybe for log calculation you might face some trouble, but that is where the Gini measure is also there, right? The Gini measure does not have any log or anything, so that is even more easier to calculate. So once you have the gains, then it is a matter of just take the maximum gain, look at the features. So I see that Overcast has four. I have four instances of Overcast, and all of them have the same output value. So I just go and create this. Yes, right. So the thing is that if you had started with humidity here, right? So here you can see that Overcast has four items and maybe that's the maximum number. So maybe I should start with Outlook. But say for some reason you started with humidity, right? Then you would have had high and normal, and then Outlook would have come, and this Overcast thing would have been distributed all over the place. So this is that would have been a much bigger and much more complex tree, right? Which is not required, right? So this is a smaller and simpler tree, which is easier to understand, right? So if you go by the information gain, then it is always better. It will give you the smallest tree which you can make.
So we have calculated the gain using some computer.
Yeah, I mean
No,
every
we are doing it with hand. Na? I mean,
hand for now we are doing it with hand, but ideally you would do all of this in a computer.
mm,
Yeah, so no one needs to calculate these gains by hand. Like this is very simple for a computer to calculate. This is just a sum. You can easily get P of C. Like P of C is just counting, right? Like how many entries are there, which have
This
like
this temperature
yeah.
feature is not used anywhere.
Temperature was not required in the end, right?
not
We
required.
could we could form our decision tree with
14 data sets
ha
where
with 14 data items, just with outlook, humidity, and wind, right? So,
Okay.
in here, so this wind is the feature, right? So in this wind feature, if it was weak wind, and say I had like three items here, two of them were yes and one of them was no, then I would have had to look at temperature also, right?
Okay.
But here
Good.
wind had only one item with the answer as yes, so I have formed this bucket, right? I don't need temperature anymore. So unless you use it, I mean, unless you need it, you don't need to use all the features. Matlab, it is not necessary to use all the features.
Okay.
Okay. So this was a decision tree. So if you see in the lecture, so the from rainy they had directly calculated, like they had directly gone to this wind feature without considering humidity.
Humidity.
One more.
Yeah, but
One more thing.
yeah, yeah, sure.
The PPTs are not available in under week 3 lecture notes. Something else
Sorry.
is coming.
Oh,
Under week 3 lecture
in
notes,
the
something
in
else
the
is
NPTEL portal, is it?
NPTEL portal.
Okay. Um,
We are not able to download
so
actual
just
lecture PPTs.
1 second. I will have to see. Yes, here. So week three, right? Week three
Yeah,
lecture
lecture notes.
notes. I
Some
got
other
signed
lectures
out.
were
Sorry,
uploaded there.
I got signed out of this account. 1 second. Yeah, okay. Lecture notes.
There are
What is
around
that?
16 PPTs. Nothing is related to actual presentations.
Oh, is there no?
It's there. It's there.
I mean,
Okay, but I'm seeing something else. I will check
okay, okay.
once.
So I think you went to this lecture
Forms
notes
about
at the end.
vegetation, digestion.
Okay, okay.
Just go to week
Last
three.
one.
There will be
Yeah,
lecture
yeah.
notes here. There you will
Hmm.
find this. So
Okay,
this last one is from like these two basically. You might get confused.
Hmm.
Like these are from some
Yeah, yeah.
tutorial sessions from last year. So
Okay.
those are not like if you want to go through them, they have some questions and all. If you want to solve them,
Hmm.
then you can go through them. But if you want, like the content is there. So for every week you will have this
Okay.
lecture notes inside it. So
Okay.
there you will find the content. Okay. Okay. I'll just quickly
Okay.
wrap up this presentation. Sorry, it's going to be beginning. Okay, so yeah, this is the fast, like the last thing which I wanted to discuss, which is the proximity matrix. So someone had asked me a doubt last time about proximity matrix. So the proximity, so in cluster analysis, so before the professor discussed cluster analysis, we had our discussion on distance metrics, right? So a proximity matrix is used in hierarchical clustering, right? It is used in
Yes, yes.
hierarchical clustering. Okay, so it's used in hierarchical clustering. How we calculate the so it is calculated from the distance metric. So we will have some particular distance metric for our problem. So for now we will just consider Euclidean distance. Okay, so which is distance from one point to another, just normal, like using Pythagoras theorem. Okay, so the proximity of two clusters. Basically, how you measure, how you create this initial proximity matrix is, so in hierarchical clustering, for the agglomerative case, so we'll start with a bottom up approach, right? So we'll start with our points, only our points. So let's say I don't have C1, C2. So let's say I have 5 points, not 5 clusters. I have just 5 points, right? So I will calculate the distance, so I put them in this grid, so in this 5 by 5 grid, and I will calculate the distance. So C1, this is, so the diagonal is always 0, right? Because like distance between C1 and C1 is 0. So distance between C1 and C2 will be some value V1. So C2, and so this is also V1, this V2, this is also V2, right? So this is a symmetric matrix. right? This is V3, V3, this is V4, it's also V4, right? This is V5, 5,
Do we need to take only
6,
the upper triangle
V6.
or something?
Yeah, I mean, the distance between C1 and C4 is the same as that between C4 and C1, right? So
It's a
this
diagonal
will,
matrix.
so it will always be a symmetric matrix with the diagonal as 0. So if you want to really like make efficient use of your memory, then yeah, you just consider this upper triangular matrix or this lower triangular matrix and continue, right? But in general, okay, so we calculate all of these distances, we have all of these values, and now we'll form our clusters based on the closest distances, right? So say C1 and C2 are closest, so I'll put them in one cluster, right? So that
How do we
becomes,
know which are closest?
the values will be smallest, right? These values are the distance values. So we have some distance metric. For now, it is the Euclidean distance. So if the Euclidean distance is smallest, I'll put those two in a cluster.
No,
And
Euclidean distance, you mean square root of x1 square minus
yeah,
xy1 square
yeah.
plus x2?
So I have 2 points, right? And the distance
Yeah.
between them. So that is my Euclidean distance, right? So say I have a collection of 5 points like this. Okay. So I will calculate. So say this is P1, right? Okay, I'll mark all of them. P2, P3, P4, and P5. So I'll calculate all of these distances like like between all of these points, put them in this matrix. That is my proximity matrix, right? Now I see that P1 and P3 are closest, so it is even smaller than P1 and P5. So I'll put P1 and P3 in one cluster, right, and call it one, so C1 or something. Okay, then I see that for the next closest to are P2 and P4. So I'll put those two in a cluster. Right, sorry, let's say P4 is here. Okay, so I'll put those two in a cluster. Then yeah, I mean P5 remains by itself. So again, so for the next step, I'll calculate the distance between. So P5 gets its own little cluster, right? So for the next step, to calculate the distance, I'll calculate. So for this C1 and this C3, let's say. So C1 and C3, what we'll do is we calculate this distance. We'll calculate this distance, take the average. So that is the distance between C1 and C3 in the next step. In the next step, I will have a 3 by 3 matrix, right? So in the next step, I will get a 3
Yeah,
by
you'll
3
have a 3 by
matrix.
3.
So this is C1, C2, C3, C1, C2, C3. Again, this is all 0. Right. So then, uh, so for C1 and C3, basically, so this value or this value, whatever. So this value will be distance between P1 and P5, distance between P3 and P5, their mean. Okay. So whatever that value comes, so even again, so this is right? So then the distance between this C1 and C2 maybe. So this is my cluster 2, C2. So that will be again. So P1, P4, P P1, P4, P like P1, P2, P1, P4, P3, P2, P3, P4. The distances all divided by 4, right? So that will be my V2 or something. Okay. So again, and distance between C2 and C3 might be something. Okay, so it's the same. So for the proximity between two clusters is the mean of distances between the instances in those two clusters. Okay, so this is always the mean of these distances, or the mean of all of those four distances, right? And it is recalculated. So this matrix is formed at every step. It gets smaller and smaller in every step because we are making bigger and bigger clusters. Now I see that maybe C1 and C3 are closer, so I will form a cluster based on these two, and C2 remains in its own little cluster. And so this is, and then like the final cluster is just one big cluster of all of them. So that is how agglomerative clustering works, right? So you have the smaller points initially, and then you cluster them into bigger and bigger clusters, right? By using this proximity matrix. So that is how proximity matrix works. Does anyone have any doubts in this explanation?
Like for example, it is C1, C2.
Yeah.
C1, C2 are, if it is C1, C2 are clubbed, and then distances of C1, C2 from C3, C4, C5 are calculated, is it?
Yeah, so if okay, so okay, let us come to this. This is a better diagram. So if I so after calculating proximity matrix for this case, I see that C1 C2 is closest. So C1 so say C1 has 2 points here, C3 has like 3 points inside. This guy has 2 points. This guy also has 2 points. I'll just assume 2 points. So now that I have this cluster, and so say this got only 1 point. Okay, and say I've clustered this as well. So after this, so from this step, I calculate all my values. I see C1, C2 is the closest, so I cluster them. C3, C4 is the next closest, cluster them. Now in the next step, what we'll do is, so if you want to calculate proximity, then you have to calculate each of these distances. So between all of so now you don't calculate the distance between C1 and C2. Now you go for so this sorry
I say C1,
this
C2, and then
distance.
C1, C3, C4,
Yeah.
C5. It's like that, huh?
So this will get maybe its own little cluster on its own. So it just stays on its own basically. So like we always go for pairwise clustering. So if you end up with an odd number of clusters at any step, then for the remaining time, like you will have one cluster which has only one, like this cluster does not change basically. So C5 does not change, right? So but I'm telling that, so for the next step, so this is my big cluster and this is my big cluster. So this big cluster has 1 2 3 4 5 points, this big cluster has 1 2 3 points, right? So I will need to calculate all of these distances. So this one, right, then 2 and 3, 2 to C4, sorry, then this one and this one and all of these distances I will calculate again from everywhere, and then I'll take the mean of all of them, and that will be my value for the distance between these two big clusters, big red clusters, right? And if I want to calculate distance between this C1 C2 cluster and C5 cluster, again like every point ka distance I will take and take the mean. So that is how it goes. um, yeah, does that make it a little bit clearer?
So when you are clubbing two, you are taking the mean of the distance between them. Two clusters, if you are clubbing,
Two
then
clusters if I'm clubbing. So how I will club them is based on the distance between them, and how I calculate the distance is by this mean method. So every point of one cluster to every point of another cluster, I have to calculate the distances, and I have to take the mean of those. So it sounds very hard to do by hand, but for a computer, this is also a very trivial task. I mean, this does not take up much time or computational space. So a computer should be able to do this clustering very fast. So yeah, this is all that I had to discuss. If you have any more doubts, then yeah, sure, go ahead. In any part.
is it the distance matrices or distance metrics?
Metric, not matrix. Metric. So metrics, like plural of metric. Metric is basically
Okay,
like the it's a measure, you can call it a metric.
yeah, yeah, correct.
Yeah.
But the problem says there's a distance matrices between data items.
Sorry, where is that?
I'm talking about the homework problem, the last problem,
Homework problem. So
last one, inductive based, yes, the last problem.
So it might have been a typo or something in that. I haven't looked at it. Yeah,
But this looks like a matrix actually.
data items and so-called proximity matrices between clusters. Distance matrix for okay, okay. So like initially like you start off, so we have these 6 points. Initially you just start with the points, right? So that proximity matrix you can call a distance matrix, like because it is just a matrix of distances between the points, between every point, right? So distance between a and b is 1, distance between a and c is 4, a and d is 2, like that. Distance between a and b is 1 again. So like distance between b and c is 2. Okay, distance between b and d is 4, like that. So this is also a proximity matrix, but
No,
since
is
this
distance
is
between B and C 2 or it is 1?
distance between b and c is 2, right? So c is here, b is here, 2. Here also it
No,
should
but
check
B
out.
starting with 1, no?
So that is the distance between a and b, right?
No, distance between A and B.
Yeah, so this is the
Yeah, the
intersection
next
of a and b, right? So this is 1.
the intersection of B and C is 2, correct? But B is at 1, na?
B is at 1 means
B value, the row which is corresponding is 1, no? Which is corresponding to the column C is 1, no?
I don't get the question.
You continue, please. Yes, understood. Yes.
uh, I didn't get your question actually. So like
Yeah, B is now A and C is 0, 4 minus 1 minus 0. C is 4 minus 0.
oh, no, 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 no. This is not the, this is not coordinates. These are not coordinates or anything. So these are like, this is the so A is at some point, B is at some point. So say A is at the origin 0 0, B is at 1 comma 0. Okay, so the distance between them is 1, right? The distance between the point A and the point C is 4. Okay, so C might be somewhere. So C might be anywhere, right? C might be what it can be. What can it be? Uh, it can be anyway. Like it can be 4 comma 0. It can be 0 comma 4. I should not have taken A as origin, but whatever. So like this is not like this is the x coordinate or y coordinate of C. So this value is the distance between point A and point C. This value 2 is the distance between point B and point C. So if B is at 1 comma 0, okay, then C is like at a distance 2 away from it. Okay, so this is not the x coordinate or y coordinate of C or B. So this is the like distance between 2 points. That's it. So like
How do you club it? It will club it into three A, B, C, D, and E, F, is it?
yeah, so that is mentioned. We assume three clusters A, B, C, D, and E, F. Okay. How does the corresponding proximity matrices between these clusters look like? So once you club them, then like you will have like A, B, C, D, and E, F. Yeah, like the options are already there. So you will have A, B, C, D, and E, F. So you have to calculate distances between A and C, A and D, B and C, B and D, and then like I mean you already know the distances because they're given in this matrix. So from there you can calculate the and then take the mean. So from there you can calculate what the value of this should be, right? So A, B, and C, D. This should be 3 or whatever.
No, do we take A, B, C, D, and E, F, and or we only take A, B, and then with A, B we find out C, D, E, F, and then we simplify it to A, B, C, D, and A, B, C, D, E, F, and then finally A, B, C, D, and E, F, and A, B, C, D, E, F. It's like that. Iterations. What do you
Acha,
mean
you're
by that?
talking about iteration. So in the question, you don't have to go any further than this. If you want to make more clusters, so say like I don't know. So say this was my final. proximity matrix. So then if I want to if I want to cluster it even more, okay, so I will go for like the closest value here is 2, so I will club A, B and C, D into one big cluster, and EF will remain in its own cluster, right? So
Yeah, that's what I'm asking.
yeah,
So it can it be
next
like that?
so that is how it is. So the next, in the next iteration we will have like two clusters, and then like if you at any point if you have two clusters, then the next iteration is club both of them into one big cluster, that's all. So initial clustering is already said over here.
Clearly given. So
Yeah, so we
we
don't
don't
need
need
to
to
think about it. We
think
just
about
have
it.
to calculate distances, find proximity matrix. In the next step, the lowest value will have like the two clusters with the smallest distance. They will be clubbed into one big cluster on their own.
So it's like four plus two by two is it is like that. Distance is two, no?
Uh,
CD is 4 and 2.
4
So
and
you
2,
take
right? So A and C is 4, A and D is 2, B and
yeah.
C is 2, B and C is 4, B and D is 4. So you add all these 4, divide by 4, you get your number, whatever it is.
Okay.
Okay, I should not be discussing the assignment
No, that's
problems.
okay. I mean, like that
Yeah,
doesn't give me
yeah,
anything
yeah.
actually.
So
So,
anyway, so yeah, that is how it is. Yeah, that's right.
okay. Thank you.
Okay, any more doubts, guys? So from any part of the presentation also, or from any of the professor's presentations? Okay, I'll check the this thing,
This is also good.
chat, like you. Okay. So if you want to type your doubt, you can type it also and check it.
Tomorrow you are only taking or some other
No,
person?
no, no. Tomorrow, one of my fellow, like another TA will be taking the
Okay.
session. I take sessions only on Mondays.
Okay.
So there are two more sessions.
Only 2 days, two sessions only in a
Uh,
week.
no, there are three sessions. So this Monday,
Three
Tuesday, and
sessions. Yeah,
Saturday.
actually I missed one session. Yeah,
Okay.
Friday and Saturday.
Yeah.
Friday,
No, no,
Monday, Tuesday.
not Friday. Tuesday and Saturday. So tomorrow
Yeah.
and Saturday. Monday, Tuesday, Saturday. These are three slots.
Okay.
Okay. So the timings are there in the course. So this announcements are made every week, but I mean it's the same time and the same link. So
Yeah, yeah.
yeah. So I think the notification for, yeah. So there's one on Tuesday. This is
Yeah,
the
it is
link.
there.
Monday is there.
The
Saturday is there.
We are getting email notifications also.
Oh, okay, okay. Then so yeah, yeah. That's even better.
so week 5 has this Q learning, and then it has got the Monte Carlo.
Yeah, yeah. That's right. So week
It
five
has got
will have.
the explanation based learning,
Ha.
and it has also got the inductive
Yeah. In
ILP.
inductive logic programming. Yes.
Yes, inductive logic programming.
Yes.
So this explanation based learning, I think, requires little bit of
Sorry.
I need to understand explanation based learning.
Okay. I mean, I will obviously discuss that.
Yeah,
But
next
okay.
week would be that only.
Okay. Yeah, yeah, yeah. Next will be that. I'll make sure if there is anything specific that you want to understand, then I'll focus on that a little bit. I'll keep that in mind basically. So otherwise, yeah. In general, I will cover everything which is there. So I'll also solve some problems.
Yeah,
Okay.
in the Q learning, yes, also you can maybe
Okay,
modules are
okay,
there.
sure. Sure, experience based learning and Q learning, right? Yeah, I'll definitely focus on this. No problem.
I had to to struggle a little bit with the Monte Carlo reinforcement technique, but finally understood.
Okay.
Uh,
Yeah, that is
yeah.
a little bit difficult, I would say. Okay, so I don't think people have
No.
any more questions. So, okay, I think we can end the session. We had a nice session. I hope you understood everything. So, if there is anything, then yeah, I mean, discussion forum is always there. I keep an eye out. I try to answer questions there. If you have any more doubts on that, you can put them in the forum. I'll try to answer them. Okay. So, yeah, thanks, guys. See you next week again.
Okay. Okay. Bye.
Bye bye.